I feel fortunate too to be here, and I thank Professor Law for inviting me, and I thank you for being here. And I am kind of thinking about this lecture as more of a. So I sat in on Professor Mani Sarathy's lecture this morning, and he write down and say, here's the Arrhenius equation, and that this is how we solve it, and how we solve differential, the couple of differential equations to get the kinetics. And I was thinking about this, what I'm going to talk to you about this afternoon is not something that's solved. So I'm going to just actually present you with a whole bunch of information and kind of my synthesis of that information. And I want you to feel challenged to think about it on your own and maybe come up with a different explanation for what we see and what we know and putting it all together. And I'll even present some of the controversies in the field, and we can argue about it. I'm happy for people to tell me I'm wrong, because that's when I learn the most, and that's when I have the most fun, is actually figuring out when I'm wrong and then trying to figure out what the right answer is. Okay, so the other thing I want to point out is you're here in person, and you're here in person not watching the video online for probably multiple reasons, right? And one of those reasons is, one, to interact with the people who are lecturing. So I really encourage you to ask questions. Interrupt me if I say something you don't understand. Interrupt me if I say something you think is wrong. I'm happy when people do that. And I also want to encourage you to meet each other, because this is an opportunity for you to build your community. And I think this is like one of the best opportunities for you to meet people now in your career, here where you are all together studying the same topics and having an opportunity to discuss with each other. And I guarantee that some of the people you meet here are going to be people you are going to know the rest of your career, people you can bounce ideas off of. And that is like so probably more valuable than anything I'm going to tell you today. Okay? So let's go through this. I'm going to welcome you as going through this material together with me. Okay? So what we're going to talk about is soot formation, starting with soot formation, but then we'll eventually go into soot evolution, how the particles, when they're first formed, we talk about how they go from the gas phase, like we start out usually with a gas phase fuel, and then something happens and they become a condensed phase particle. So we'll talk about that. And then how those particles grow, how they evolve during the whole process of soot formation. They start from like one form and they change dramatically over their lifetime in the flame or during pyrolysis. And then they get spewed into the atmosphere and they change some more. So we'll try to do a little bit of all of this over the next 3 days, okay? So there's gonna be a lot of material, and if you were in Professor Sarathy's lecture this morning, I have about 5 times the number of slides that he does. So some of it might go fast, but please slow me down if I'm going too fast, okay? Okay, so let's talk about where we're gonna head today. So the first topic is soot chemistry. And I'll tell you, I'm a chemist by training. I get my PhD in chemistry. But chemists usually, like, all the great advances in soot formation are taking place in mechanical engineering, because chemists are afraid to touch this problem. It's so hard. It's like the molecules are big. The chemists are like, I want to deal with a diatomic, a triatomic. Once you start to get to soot formation, it is a hard problem. So it takes the courage of an engineer to actually tackle this problem. So you are in the right place. This is what you can be working on and making progress, because it's still a really open field. We definitely don't know everything. So I'll be talking about overview, kind of like why do we even care about this? And you might think of soot as just completely bad, but actually soot has a lot of good aspects too. I'll talk about that. Then we'll talk about soot inception. That's the that part where you go from a gas phase to a condensed phase particle. That's inception means birth. So that's when the particle is just birthed, okay? And that has a lot of controversy associated with it. We're still trying to figure out what's going on. Then I'll talk about how the particle grows and evolves, and particles go through kind of a life cycle, like almost like I try to kind of, it's analogous to you being born and then evolving into a young person and then aging, and so we'll talk about how that happens. And then soot oxidation, all part of chemistry. So later in the week, we'll talk about soot diagnostics, and there's a whole host of diagnostics that are available to us to look at soot in all its various forms, but there aren't enough. So this is where we have more growth that can happen, more innovation that can really change the field. So I'll be talking about what we do have, and then kind of highlighting places where we could change and grow. And then at the end, I'll talk a little bit about the environmental impact of soot. Once it gets emitted into the atmosphere, what does it do? Where does it go? What are the negative aspects of having it up in the atmosphere? And how can we think about that problem? Okay, so let's start out with what are the positive aspects of soot. So soot is a well-known ink or dye. People have been using it for tattoos for thousands of years. So there are mummies that have been dug up with tattoos that were generated by injection of soot into the skin. And we're still using some of that technology today for tattoos. So when it comes to tattoos, they're not regulated. So the dyes that are used in tattoos are not regulated. And soot, like char material, is actually used in tattoos. And it's been used in art form for forever. In fact, when I was doing an experiment at Berkeley, an artist asked me if she could take the soot we were generating during our experiments and use it in her art, and she actually has been generating art. I have one of her pieces on my wall, and she shows it in galleries, so I think that's really fun. And it's used as, you use it all the time when you're printing something out. If you print anything out anymore, it's used like all the time, but now we all do everything online. It's also a filler for rubber. So in tires, it's a reinforcement in tires. We actually use a lot of soot in the form of carbon black in plastics. You've been touching products made with soot all morning. Most of the black plastics you see have soot in there as fillers. Rubber, pretty much everything has a soot. I think it's an $11 billion industry, and it's an industry. It's called the carbon black industry, and this industry is changing. This industry needs new ways of doing things, and people are trying really hard to generate black carbon in an environmentally green way right now. So this is an industry that's evolving with time, especially right now. And it's used in cathodes of lithium-ion batteries. It's used for heat transfer in industry. So if you're making glass, you want to have soot. It's going to distribute the heat in your glass furnace because it radiates. This is one of the reasons we need to understand soot radiation, because if we want to be able to control radiation under different conditions and different industrial processes, we want to understand it. So it's used in furnaces and boilers. And it's all, I just was looking online, like, what are all the different uses? People are using it in different applications. This is one I found for pulse generation of ultrasonics. It's just generally like a material that you can, largely because it's black, and it just absorbs light really strongly and then emits light. So you can, kind of calculate what you need, and it's very effective at transmitting light or radiating light. Okay. You can use it as an amendment to soil in water. Under some conditions, it can filter out kind of like, activated charcoal is a good filter for pollutants. Soot can act as a little bit like activated charcoal under some conditions, and people have been investigating whether or not it can be used as an amendment for soils to make it more bioactive or bioavailable, increase fertility of soils. And then, of course, it makes great sunsets. I don't know if you've noticed it during, after a forest fire, some of the sky looks pretty darn beautiful with this red sunset. But on the flip side, it actually has a lot of negative impact, right? And you're probably really familiar with how all the negative impact it can have. So, first of all, it's not, when you put it in the soil, it's not all that bioavailable. So even though you might want it to be, some types of soot can be, some types of soot can't be. So it depends on how the soot evolves under your type of process you've generated it. So we'll talk a little bit more about that later today. It can contaminate water supply after a wildfire. So I'm actually working with some water toxicologists trying to understand and be able to predict how much of an impact soot can have on water supply. And in some of these places where there have been large wildfires, the water actually tastes really awful after a wildfire. And that's partly because it also absorbs a lot of other species that don't taste or smell that good. And then it can, under extreme conditions, it can totally take out that sunshine. And so in Colorado, we've had a lot of problems like that. So negative health effects, of course, it increases risk of pulmonary diseases. So asthma, emphysema, chronic bronchitis, you're probably very well aware of these issues. And actually, those images to the left, those are TEM, transmission electron microscopy images of the lung tissue from the Tyrolean Iceman that mummy I showed you a while ago from inhaling the fires, probably sitting when he was cooking. It can have a serious effect on cardiovascular illnesses and disease, causing these diseases. So it can cause heart attacks and stroke. It can also have a negative impact on your neurological health. It's been shown to have a whole host of issues related to how soot gets absorbed into the lungs, and then the tiny particles can be transported through the bloodstream or directly through the olfactory nerve. So that is the brain cells from a rat that breathed in soot through its nose and went through the olfactory channels up into the brain. So it can go right from your nose up to your brain if the particles are small enough. And it can cause things like multiple sclerosis, Alzheimer's disease, Parkinson's disease, epilepsy. At least people have noticed a connection between them. It was the cause of the first industrial health or industrial illness related to chimney sweeps. It causes cancer. So this is from the web from 1868. It was recognized as a cause for this what they called soot wart, which is a cancer of the scrotum for chimney sweeps. You can look at that picture online. I didn't. My husband told me I shouldn't show male genitalia in a lecture, so I fuzzed it out. So, but it's actually on Wikipedia. Okay, so and it reduces your ability to control fires, right? So for fire safety, because it radiates, and so it transmits heat to surrounding buildings or trees, and it's really hard. It actually causes fires to propagate. Okay, so, oh yeah, an impact on air quality, indoor air quality, as well as outdoor air quality and visibility. And it has a negative impact, like it keeps going. I keep forgetting how many of these. It has a negative impact on agriculture, reduces crop yield. And I'm not sure if you've heard about this thing called smoke taint. this is actually a huge deal in California and in Australia, where after there's been a fire near a vineyard, they have to dispose of all the grapes, because even if they determine that what's on the grapes isn't going to cause anyone to get sick, they can't use it in producing wine because it makes the wine taste terrible, and it's called smoke taint. So this is there are a lot of people trying to look at how to solve this problem, because it's really having a big impact on the wine industry. It can reduce energy efficiency, and it causes climate change. So it is the second leading cause for climate change. It's basically like a greenhouse gas. Right after CO2 is soot. But the error bars are really large, so it might be number 3 after methane. So it's CO2, methane, and soot are the 3 top greenhouse gases, largely because these particles absorb very, very strongly over a wide wavelength range. So it's mostly when light is re-radiated up into the atmosphere, it absorbs the light and causes greenhouse warming, or global warming. Okay. And not only is it as direct radiated forcing, is what we call it in the climate sciences, it also falls on snow, lowers its reflectivity, so when sunlight hits the snow, it doesn't bounce back up to space. It gets absorbed. Then it melts these glaciers, and that actually causes more global warming. So these are called secondary effects for climate change. And then it's kind of interesting, it has an impact on clouds. So it actually has an impact on weather, but more importantly, it has an impact on high cirrus clouds and where it's emitted into the atmosphere. So this is one of the reasons I was talking about what's its fate. So it's not all like spewed out of your tailpipe when you're driving. There's also aircraft, right, that distributes soot higher up in the atmosphere, and where it's distributed has a big effect on where it goes and what kind of impact it has on the atmosphere. So that's why this is like heating and cooling effects. It depends on where it's emitted into the atmosphere, or how high it gets into the atmosphere, how big the particles are, how much they've aged, when they got out of the flame, like did they go all the way through the tip of the flame and get hot and become mature soot, or was the flame quenched early? All that has an effect on whether or not they can form a cloud, and whether or not they can make the cloud big enough to rain out. So there's a whole host of, this area in climate science is a big open area. So this is an area where, you could have an impact studying cloud formation from soot. And it can sequester carbon in soils. Okay. Okay. Oh yeah, this is, so the other thing, I don't know if you've ever seen this happen. I have a Prius, and I have seen this happen. It's called rolling coal. People have modified their engines so that they can flick a switch and it can spew out a big cloud of soot. It's so disgusting, and it makes me so upset. But on the other hand, it kind of makes me feel like someone else loves soot just as much as I do. I have a little bit of connection to the person who's doing this. And this is a guy, he's getting a soot tan, is what they call it online. Okay, so let's go back to what is soot. So there are many ways of looking at the particles that are formed, right? I have a definition I'm going to use for the whole time that I'm talking to you. The definition I go with is it's the particulate matter produced when you have incomplete combustion or pyrolysis of hydrocarbons. Okay, so this is the way you define it actually helps us, or having an understanding of how I'm defining it will help me talk to you about what I'm going to talk about, because soot will evolve throughout its life in the combustor. So if you want to just call it the black stuff, I call that mature soot. The stuff that's first formed, that's not this clear actually in the visible, you can't really see it, I call that either incipient soot or young soot. So, but I call all of those particles soot. And I just think of it as soot is evolving through its whole life cycle. Okay, so that's what I'll be using to refer to soot. And we'll talk about all the different definitions. Because this is actually another aspect of the field that's become kind of a curiosity, is that people are coming from different fields and everyone has a different way of talking about stuff. They have different words they use. And then I noticed I was, I don't know if you've like submitted papers to the Combustion Symposium, but what happens is, there will be someone who's kind of like called the chair of the colloquium on soot, for instance. And so you get all these papers and then send them out to review, and then you come back, and if you're reading them, you're like, I think the problem is this person's using this word to describe what they're talking about, and this person's not understanding. So there's kind of an interesting thing where we have a lot of controversy, mostly because of the way we're talking about things. So we've tried to go through, so I've been part of the, if you're interested in soot, you should think about, if you're gonna go to the symposium, sign up also for the international workshop on sooting flames. So I think you'll find it fascinating. It's a small group of people who like to talk about soot and think about it and figure out how we can understand it, who are trying to figure out a way to collaborate so that we can combine all of our different skills and perspectives and techniques to understand the problem. So this is important that we understand kind of the terminology, and I'm going to talk about that in a minute. Okay, so how's soot formed? The very simple picture is you start out with a fuel, maybe a fuel and an oxidizer. If you're doing combustion, you have ignition, and you generate small radicals, right? Small species. And then you have molecular growth. So usually when you have soot, you have larger molecular species, right? It's a question how large those species are. I think, we think we know, but it's really hard to tell based on our techniques for measuring. So we have molecular growth. We get up to polycyclic aromatic hydrocarbons, right? And then something happens we call inception, and those gas phase species turn into a condensed phase particle. So so how do we say, okay, this is a soot particle and this is not a soot particle? When do we draw that line? So I think we should draw that line in and this is like a fuzzy line. When that big molecular species on the right, potentially molecular, maybe not, we'll talk about that some more, when that has the properties of condensed phase. So when its density is high enough, so in a gas phase, you're gonna have a much lower density than you do in the condensed phase, right? The density will change, the optical properties will change, right? The specific heat will change. All these different properties will start to become much more like a liquid or waxy substance or a solid. That's when I like to define the transition between gas phase and the incipient particle. So that particle on the right, we call an incipient particle, the one that's just born, okay? So the transition between the gas phase and condensed phase is inception. And I was saying, I like to think of this as an evolution. And there's a whole terminology associated with this evolution. So let's talk about that. So we have the particles going from the gas phase to what we call on the very right-hand side, the mature soot, the black stuff you normally see coming out of a combustor. I like to make the analogy that we have our newborn particle is like our puppy, right? So our incipient particle is our puppy. And then our puppy will age into a mature dog and go through phases. So too does soot. So we start out with the incipient particle, and then we have a young particle. And then we have a particle that's mostly mature, and at the very right-hand side, we have a particle that's really mature. And then there are some people arguing about whether we should have adolescent particles or not, but we haven't quite gone that far. I don't know, it seems so, well, maybe we should. I could take a poll and we could decide if we should call them adolescent particles. Okay, so what are the major steps in soot formation? Let's talk about this. So we have our gas phase species, right? And we just talked about those are larger hydrocarbons, polycyclic aromatic hydrocarbons, different species. And then we transition to our first particles. Then we have, once we have our incipient particles, whatever they may be, then they grow. And this happens very quickly. So you have rapid growth, and you have fine structure evolution. So this is where you get your graphitization, what we call graphitization. You start to get order in the particles. And then the morphology changes. So that's where you go from like a single particle, they start to attach to one another, right? And then you start to have aggregate formation. And the final particle, the mature soot particle, you've probably seen TEM images of them. There's these stringy aggregates of spherical particles, more or less spherical, but not exactly spherical all the time. And then we can talk about oxidation, so we'll do that towards the end of today. Okay, so let me just give you some terminology associated with each of these stages so that we're using the same language. So we have these gas phase species we call soot precursors. You'll see in the literature, if you're reading the old literature, that sometimes people will call the incipient particles soot precursors. But I think it's clearer, and most of the literature in the last few decades has been the soot precursors are the gas phase species. Okay, so, and then we transition to these particles, and that transition, that inception is the gas phase to condensed phase. We also call inception or nucleation. So nucleation, so inception is a word that means basically the birth of the particle. And nucleation is a type of inception. So inception itself, you don't know how it's done. You just know it goes from the gas phase to the condensed phase. Nucleation implies that you have a thermodynamic process that's causing these particles to form. We don't know if it's a thermodynamic process that's causing particles to form. Like if you have a gas phase, like water, and you have droplet formation, you could call that nucleation and then condensation, right? We don't even know how the particles are formed. So we're using a term, inception means any way it forms. We just are not being specific about it. Nucleation, we are reserving for that transition that's caused by a condensation type of process where it's thermodynamically driven phase transition, okay? Okay, so, and the transition, then these particles are held together by what we call van der Waals forces. They're electrostatic forces that hold these particles together. Okay, so let's talk about the particles themselves, those incipient particles. What do we know about them and how do we know it? So some of what we think we know actually is based on some very old experiments that people are now starting to redo with better techniques and go, maybe that wasn't right. So I think we have to kind of be open-minded and kind of like let go of some of our understanding and just like, be open to new possibilities. Here are some data that were taken a long time ago. This is a TEM image from, that's actually not even that long ago, 2007, of particles. And I think this is, people have shown this that they're spherical. I'm not saying this is wrong or we have to be, I mean, I think this is actually right. They're quasi-spherical. They're mostly invisible to electron beam for, TEM imaging. It's hard to image them. They're small, like a few nanometer size. They absorb in the UV, but not very strongly at longer wavelengths. And they have a carbon to hydrogen ratio. People have measured 1.3 to 2.0, somewhere in that range, okay? They're kind of like not completely solid, probably. They're like liquid-like or maybe waxy-like. They kind of flow a little bit when they hit the grid. So here's an AFM, atomic force microscopy image. So atomic force microscopy, we'll talk about diagnostics tomorrow, but just so you can look at this image, you basically have a tip, a solid tip that goes over a surface, and if it sees something that goes up, it has a little mirror on top of the probe, and the mirror will tilt, and a beam of light is reflected off of that, and you can see actually when your tip moves up and down. So this actually gives you a physical position on a surface. So people have seen using AFM as well that the particles are spherical, but it looks like they spread out when they hit the grid, because the diameter on the target is larger than the height of the particle. So it looks like if they're spherical, then they're spreading out on that surface. Okay, so so what we call these are incipient particles. There are other words that we've used for them, nascent particles. Nascent, and that's like widely used in the literature. I don't use it so much because for if you're trying to talk to atmospheric scientists, nascent means the particles that are emitted into the atmosphere. Whereas in combustion science, nascent means the particles that are just formed in the flame. So I don't usually use the word nascent just to avoid the confusion with atmospheric scientists, because this is an area where it would be really helpful for us to be able to connect with atmospheric scientists. They can be called clusters because they're clusters of molecules. Nuclei because they may be the nucleus of another particle that's just formed, that's being formed. Or growth centers, again, the same idea, like a nucleus that's like seeding the growth of a bigger particle. And then we have particle growth. So the particles are evolving. And particle growth can happen in multiple ways. You can have particle growth that happens on the surface of the particle. And that's another open area. We don't know how that growth happens. We can also have particles that coalesce or clump together with each other. Coalescence is a clumping where if you have two droplets of liquid that are miscible, they'll coalesce into one droplet. It's when something comes together and you can't distinguish between the original two. So that's very different from coagulation, where you have particles that make an agglomerate will stick together and you can see the individual two particles. Okay. Condensation is a gas to liquid transition. So if you have, so this is another interesting one. We often talk about condensation, but if your gas phase species are sticking to your particle and they're making a solid particle, they're going from the gas phase to the solid, condensation technically doesn't describe that process. So that's a difference. So we often think about adsorption for that process. So vaporization is liquid to gas. It's the reverse of condensation. And that includes boiling. Deposition is gas to solid. Sublimation is solid to gas. Okay? And then adsorption and desorption are related, and we usually think of adsorption on somewhat of a molecular basis. And you can have chemisorption, where you actually have the molecules making a chemical bond, a covalent bond with the surface, Or you can have physisorption, where again, it's something like condensation in that it's a thermodynamically driven process through electrostatic forces. Okay. And then desorption is the reverse of adsorption. Oh yeah, I know I have this. Okay. Okay, so we have chemical evolution. And sometimes we call this soot aging. Okay, graphitization is interesting. So if you think about soot and its evolution, let's see what's, graphitization, so we often talk about soot carbonization. And sometimes we think of them at graphitization and carbonization as being the same. So what'll happen is, you're thinking about these hydrocarbons coming together and making a particle. Eventually, at high enough temperature, you're going to get rid of all the hydrogens, or a lot of the hydrogen, not all of them, but you're going to get rid of hydrogens. And we think of that just generally as carbonization. So hydrogens are emitted from your particle. Maybe there's rearrangements, and in material science we'd call defect, getting rid of defects, or annealing of some sort. If you've ever taken a materials science class, but that's not the same as graphitization, because graphite is very specific. Single crystal graphite has these planes of graphene of 6-membered rings, and you'll have one layer. Graphite will stack another layer of graphene onto the first layer in a specific orientation. And then the next layer will be stacked on a specific orientation. If you are forming graphite like that, you can call that graphitization. Some types of carbon like this cannot actually fully graphitize. So interestingly, Rosalind Franklin was a person who first studied whether or not these carbons can graphitize, doing X-ray crystallography on these different graphites. And I don't know if you remember who Rosalind Franklin is, but she was one of the people who figured out the double helix structure of DNA. She did not get the Nobel Prize. Watson and Crick did, but they used her data. Actually, without her knowing it, without her permission, they got her data from her technician. So she should have been part of the Nobel Prize. But anyway, she was doing X-ray crystallography on carbons, and that was around the same time she was actually studying what I would say is work that is really important for soot formation, understanding graphitization of these carbons. So it turns out in soot, we don't have single crystal graphite. And this is a key to how we have soot growth, actually. So in soot, we have planes of graphene of a certain size, but they're randomly oriented. They're not in the orientation of single crystal graphite. That's why when you look at single crystal graphite, it will have an interlayer spacing that's smaller than the interlayer spacing of soot. And that's why soot doesn't have the exact properties of graphite, because it has that random orientation. So you can think about how are we getting soot growth that's causing this random orientation? And on the flip side, how are we getting this material that's actually having stacking of these planes, which is also really, I don't know, I find it really fascinating, and I haven't figured it out. So no one has figured out how we get that. So what happens is we have this process, we have graphitization, carbonization. So we're getting more and more carbon. So our carbon to hydrogen ratio, remember the incipient particle is like 1.3 to 2.0 carbon hydrogen ratio. The mature soot at the end, our final product, normally has something like 8 to 12, okay? So we're getting rid of those hydrogens, accumulating carbons. Annealing is, when you're getting more and more ordered, so you have bigger and bigger sheets, and in soot you have bigger and bigger sheets of carbon of graphene, okay? And then we talk about maturity level, is how close to mature are we? And then young particles, we often call them partially mature soot particles. And mature soot particles are what we see coming out of a hot fire or a hot combustor. Okay, so what's the mature particle look like? It's what we call refractory. So it doesn't melt. It's like you can heat it to really high temperatures and it will like kind of keep stay what it is. And if you heat these things up with a laser, you can get up to about 4,000 Kelvin before you sublime the carbon. So these are pretty solid, strong particles. The density is close to 1.9, 1.8 to 1.9 grams per cubic centimeter. The mature particle, as I was saying, absorbs very strongly over broad wavelength range. Again, it has a carbon to hydrogen ratio of 8 to 20 is closer to what you get when you have carbon black when people are manufacturing the material. So normally in a flame, I think is 8 to 12. If you're just light a co-flow diffusion flame, it's probably about 8 to 12. Okay, and then these aggregates are made out of primary particles that are 10 to 50 nanometers in size, approximately. Okay, so you have this aggregate, your mature particle, and it's held together, right? It's held together very firmly. If you hit these things with a laser, you get sublimation of the material. The carbon atoms come out in like C2 and C3 without blowing apart that aggregate. So these things are held very, very firmly together. And if you see, the way the structure of these primary particles inside the aggregate is kind of in disordered center. So let's see, I think. You have these disordered foci or growth centers that are a few nanometers in size, and then over the outside you have this turbostratic graphite, layers of disordered graphite, and they're in like crystallites of varying sizes depending on how mature and ordered they are, and they preferentially line parallel with the surface. I mean, it's beautiful. It's like, and it doesn't matter what kind of combustor comes out of. It's incredible. It's like these little seeds of these little pearls of soot. I mean, I just can't get over. It doesn't matter if it's coming out of a forest fire or your diesel engine. You're getting these types of particles, and this aggregate has the same morphology independently, generally, mostly independently of the combustor. This is incredible. So here's why you should feel optimistic about the future. There is something that's simplifying this whole process that, it's not that we have to solve every single chemical equation and figure out what's going on, because there's something simplifying how we're getting this soot because they all come out the same. There's some rate limiting step that's causing all the particles to look the same. Some basic mechanism or process that it doesn't matter really what the conditions are. We haven't figured out what it is yet, but that means we can figure it out. That, once we put our heads together, we can actually figure it out. So I'm optimistic that we can sort out how soot is made. And once we sort it out, I think that leads us on a way to help mitigate its impact, okay? And also use it for generating particles we really want. Okay, so we have our morphology evolution. We start out with a single particle. Our primary particles, which are the elementary blocks of these aggregates. We have agglomerates. So what happens is these primary particles come together. They stick together. So the difference between, so remember this, the difference between an aggregate and an agglomerate is agglomerates can fall apart easily, aggregates are stuck together. Okay, so when you're writing a paper about soot, think the mature particles are aggregates. In between they're agglomerates. Then they form aggregates. And they have, so morphology is the shape of the final particle. And we usually call that shape dendritic, or ramiform or ramified. They're different words. And then these aggregates can restructure. So when you coat them, for instance, when like a particle that say comes out of an engine. So if you're listening to the lecture this morning by Professor Mani Srathi, if you had a particle coming out of a marine engine, right, a ship, high sulfur fuel is going to have sulfuric acid. Sulfuric acid is going to coat the particles, and they'll clump up. So they change their form. That's called restructuring. So I think I have an example here. Yeah. Oh, yeah. So let's see. Okay, back to this. And oh, yeah. The way you get the aggregates is you have graphitic overlayers. So this is why you have aggregates that don't fall apart, is you actually have, as the particles are growing and depositing, I think they're depositing carbon on the outside. And so you form the agglomerate, the young particles go boom, and stick together, and then graphite forms on the outside of those particles and covalently binds the particles together. Okay? That's how you form the aggregate. I guess I don't have a slide that shows the restructuring, but they will clump up. And that changes their optical properties. That changes their reactivity. That changes a lot of the properties of the particle once they restructure. Often it's restructuring in the atmosphere, but sometimes in the exhaust. Okay, so fragmentation happens when you have oxidation. That's where the particles break up, okay? Okay, so we have our transition, we have particle growth and aging, oxidation. So here are the questions. What are the mechanisms for inception? So we're going to be talking about these questions. How do we describe the first particles, right? What are the mechanisms of particle growth and aging? How do we describe particles as they evolve? So these are some of the things we actually just covered. What are the mechanisms for oxidation, and how do we describe particles as they oxidize? So we'll talk more about some of this next, actually, coming up. Okay. Okay, so mature soot particles, between inception, when you have the incipient particle, and the evolution and growth, the mature particles, we end up having multiple processes we were just talking about. So we have surface growth, carbonization, and some degree of graphitization, not full graphitization. We get coalescence, so this is kind of a review of what we just went over. We get coalescence that can cause growth. Also surface growth can happen. We get agglomeration, forms the agglomerates. Those can be pulled apart, right? Then we get aggregation because we have this overlayer of graphene, or multiple layers of graphene. So when people talk about necking in the community or bridging, that they're talking about how the graphene has grown between these particles. And then if you look at the particle, a lot of times the primary particles won't look spherical. They're kind of oblong because you've grown stuff in between them. And then we have oxidation. And then once the particles are generated, you can have coating, you can have restructuring. And then in the atmosphere, people often study atmospheric emission and aging. Okay? I should keep track of the time. Okay, 3:15 is our break. So if I start to get close to 3:15, just remind me to, we'll do a break because I want you to stand up and stretch. Okay. So over this time, our particles are growing like crazy. They're going from a couple of nanometers all the way up to hundreds of nanometers, and it depends on your process. Wildfires have huge particles. Diesel engines have more like 150 nanometer sized particles. This all happens over milliseconds, tens of milliseconds. Like the inception part is only a few milliseconds. So you're having these particles just like grow like crazy and evolve over that time scale. And what's happening during that time is you're growing in size, your morphology is changing, right? You're like dramatically going from basically a gas phase to this like clumpy stuff. Consistency is changing, so you're starting out, possibly liquid-like, maybe waxy-like, to this solid, like hard, like graphite type stuff. Carbon-hydrogen ratio is changing, so you're spewing hydrogens out of your particle. The fine structure is changing, so you have basically, when I say long-range order and fine structure, that means like if you start out with one benzene ring, increasing the order is like adding rings and making that size, that sheet size bigger. The density increases significantly, and that's the density of the material in the primary particle. That density is changing, largely because you're pulling hydrogens off and you're getting order, and they're like the interlayer spacing is getting smaller. The surface reactivity is decreasing, so when you get to the mature particle, it's less reactive than the incipient particle, and the optical properties change like significantly. Okay, so that's the basic overview of what we think about when we think about soot. Okay, so let's start talking then about the chemistry of soot inception. So this is kind of one of the areas that's the most controversial, where we have, people get pretty excited about it. And their arguments can break out in the middle of meetings about soot inception. Okay, so they've made a whole movie about it. I mean, this is like, it's a big deal. Okay, so our incipient particle, what is its size? Let's just go through and look at like more details of the measurements that we have. How do we know what we know? Okay, so here's an experiment where this is a very common, some of you might even have this type of burner in your labs. So you have a stabilized, one of these stabilized burners where you have like a premixed flame, a laminar premixed flame, and then a plate that stabilizes the flame with a hole in the middle. And then you send nitrogen through that plate in a little area in that plate, and it extracts the soot and whatever effluent you have, and it goes down that tube to your measurement, whatever your measurement is. And the idea is that the particles go up, go through that hole, and then they're instantly diluted and cooled. So you quench all the chemistry that's going on so you can see what's happening to the particle. And then if it's dilute enough, you're not going to have collisions between particles so that you can get their size. Okay, so this is an experiment using one of those, that setup, with a scanning mobility particle sizer. And we'll talk about more about that technique tomorrow, but for today, just know that it's a measure of size. Okay, so you can see at the bottom, it says diameter in nanometers, so that's the x-axis, and on the y-axis is basically the size distribution, the size, number of particles in that size bin. Okay, so you see that low, and then each of those is different heights in the flame, so the plate is moved up as you go from the bottom to the top of the figure. So in the bottom, the height above burner of that plate is 7 millimeters, and at the top is 12 millimeters for this particular flame. Okay, you see that the peak at the lowest is just a few nanometers in size, right? And then as you go up in height, you start to get bigger and bigger particles, and then you actually look like it's a bimodal distribution, and you get a larger sized particles. This is really common. This type of size distribution as function of height of a burner, HAB, is really, really common. Okay, so the particles on the left, like those small particles, those are probably our incipient particles. They're formed first low in the flame, and then as they go up in the flame, they're going to get bigger. They're going to evolve in the flame. okay? And then then the question is, what is that second? So that's our incipient particles, less than about 2 nanometers in this experiment. The second mode is something, but we don't know what it is, right? So I'll show you some data where people have been trying to figure that out. But, could be, if you think about it, maybe you take 2 of those 2 nanometer sized particles and you coalesce them. They become 1 particle, right? But there's some reason that they're forming a second mode. Okay. And people see it in other experiments. So this is another experiment. See the first mode. You see the second mode. The arrows are pointing to the first mode, the second mode. That peak over by less than 1 nanometer, that's an experimental artifact. So this is something that we have to be careful of. This is produced by the probe, how you do the probe, okay? So this is stuff that kind of messes us up, right? These peaks that we over time identify as this, but it turns out to be an artifact, right? This is, and we'll talk a lot more about this tomorrow. What are how can we get tripped up when we're trying to study these particles? Okay, so yeah. So here's another experiment. Instead of a scanning mobility particle sizer, now this is a photoionization mass spectrometer. So they suck particles out of the flame. So it's also premixed flame. But in this case, they have a probe that sticks down into the flame. And then they move the probe up and down in the flame. Or on the right-hand side, they're actually changing how lean or rich the flame is. So the C to O ratio, right? Equivalence ratio. And they have marked it as C, number of carbon atoms versus number of oxygen atoms. Okay, so if you notice, you still have the same bimodal structure. Again, you have that weird peak over to the left that's an experimental artifact, right? And this is a completely different group with a completely different technique. And notice, too, that it's sensitive to C to O ratio. So at the lowest C to O ratio, you just first get that little initial peak, not the second peak. Okay. Yeah, so there's what we think are incipient particles, that first mode. And then there's that second mode. Okay? Yeah. Okay, so just from looking at a lot of these types of experiments, you can say that the incipient particles probably are a few nanometers inside. They form at lowish carbon to oxygen ratio. That depends on fuel as well, like the exact C to O ratio depends on fuel. They form at low HEBs, and there's a second mode that comes in. And it appears that you first see that small mode, and it may be what's causing the second mode. You don't just suddenly see the second mode popping up at larger sizes. You see that first mode first, and then that second mode. If you think of if you're following the fuel up in the flame, okay? Okay. So this group, the Grothier et al., did some experiments. This is a couple of different experiments where they tried to figure out what those 2 modes are by photo. So when they do their experiment, so I told you they suck out of the flame. And then this is a mass spectrometer. So in order to do a mass spectrometry measurement, you have to ionize. In this case, they're not taking the particles apart. It's not an aerosol mass spec. They're just taking the particles and ionizing them. So they ionize here they use an excimer laser, and they ionize at 193 nanometers. So now you have ions, and then the ions are generated in a field. So they basically pulse this field and inject the ions down this flight tube. And the larger ones, if everything has one positive charge, then the smaller masses will get to, you're applying a force, like when you pulse, you apply an impulsive force, and the smaller masses will get to the detector before the larger masses, right? So what they've done then is, so here's their mass spec, and they said, okay, you have larger lump on the right, smaller lump on the left. What happens when we ionize with different photon energies? So this is at 193, okay? What they claim is for this 193 nanometer photoionization, it takes 2 photons to ionize the small ones and 1 photon to ionize the big ones. Okay, well that probably tells you something, and what they concluded was if you have a big like macromolecule type thing that is your small guys, it's going to be harder to ionize that than if you have stacked, stacked PAH type or graphene stacked particle. It's going to require less energy to ionize that, because if you think about if you think about soot, right? When it starts out, it's mostly hydrocarbon, and it absorbs in the UV, right? We just talked about that. It absorbs in the UV. As it evolves and loses its hydrogens, and the structure starts to form, we have stacked graphene, it starts to absorb way out in the infrared. It broadens, this whole spectrum broadens. So what they're thinking then is, okay, if that right peak absorbs just 1 photon and ionizes, and the left peak has to absorb 2, that means the right peak is probably more ordered and has less hydrogen than the small peak. Okay, that's what they were assuming. So someone else did the same experiment. And so then they concluded the incipient ones are the small peak on the left, right? They have kind of stacked PAHs type things, the structure on the right peak. And they separated those two and said, okay, we're getting these what we call young particles that are happening at higher carbon-to-oxygen ratio. Okay, so someone else did this experiment and said, no. They all absorb at 213 nanometers. There's no difference. Okay, so now we're back to ground zero, because now we have conflicting results, so we don't know. For all along, people were like, okay, well, this one's ordered, this one's not, and now we're back to ground zero. So now we have to come up with more experiments to try to figure out what's going on. Okay, I'm not gonna give you the end of the story, because there's no end of the story. So this is one of our open questions, okay? But this is an interesting one. So this is the same group, Grothier et al., a different paper. They said, okay, let's now ionize, let's hit these particles with a 1064 laser. 1064 is near IR, right? This is the laser wavelength we use for laser-induced incandescence. This is a wavelength where when we have mature soot particles, it absorbs like crazy, heats up to 4,000 Kelvin with a 1064 nanometer, okay? So let's hit these particles with 1064. And what they saw is, okay, so the black one is if they just are doing basically the experiment I showed you in the previous one, except the distribution doesn't look exactly the same. It's a different experiment. Probably not completely reproducible here, as we were seeing. And you see that there's a big peak they call the B peak, right? The one that they say is ordered. When they hit it with 1064, it heats up. What they say, it goes away. Let's say the peak goes away. That's what we see, right? Their explanation is it heats up and vaporizes. Okay, but the first peak doesn't, just the second peak. So that actually is also intriguing, right? It kind of tells you that the particles probably are kind of different. There is something different about those particles. Okay, so these are the type of clever experiments we need to be doing to try to sort out some of this, what's happening when we generate soot particles. Okay. So what they say, the ones on the right, they call them stacks. They absorb and vaporize. Ones on the left don't absorb the IR and just stay. Okay. So back to like the left-hand figure you just saw. That's our SMPS data premixed flame as a function of height above the burner. The right-hand side is the spectrum, the extinction spectrum for the particles that are in the flame. And you see that, are you giving me a signal? Yeah? Okay. Okay, yeah. Is it, okay, thank you.